Today, we're diving into a fascinating biological puzzle. It all starts with a very simple, almost childlike question about one of nature's most incredible transformations. I mean, really think about that for a second. Silk is this incredibly tough protein, right? But the super fragile creature inside makes something powerful enough to literally dissolve its own prison so it can fly away completely unharmed. How on earth does it manage to dissolve the house without dissolving itself? The answer to that is the key to this entire story. And here it is. The silkworm's secret weapon is an enzyme called serrapeptase. The real magic is right there in the definition. See, it's proteolytic, which is just a fancy way of saying it breaks down protein. But its superpower is that word selectively. It has this incredible, almost intelligent ability to tell the difference between non-living stuff like the silk cocoon and the living tissue of the creature that made it. Now, this unique ability, you can bet it caught the attention of researchers. Japanese scientists were the first to isolate it from silkworms way back in the 1950s. And get this, by the 1960s, it was already being used clinically over in Japan and Europe. And today, we're still studying its systemic effects, that means its effects throughout the entire body, on things like inflammation and other problem-causing protein structures. Okay, so to really get why this little enzyme is such a big deal, we first have to talk about the problems it's perfectly built to solve inside our own bodies. Because, sometimes the very proteins that are designed to help us they can overstay their welcome and cause some really serious issues. Let's take a look at a perfect example, a protein called fibrin. Fibrin kind of has two different faces. On one hand, it's our body's heroic first responder. It rushes in to form clots and scar tissue, walling off damage. It's absolutely essential for survival. But when it sticks around too long, it becomes a real problem. This chronic excess fibrin can choke off blood flow, make our tissues stiff and rigid, and even create these little shields for abnormal cells to hide behind. And it's not just fibrin, there are other problem structures too, like biofilms. The source material uses this fantastic metaphor to describe them, and it's perfect. Slime armor. It's just such a great way to picture this protective shield that can hide all sorts of things we really don't want hanging around in our bodies. So what does this slime armor actually do? Well, it basically builds a fortress. It hides nasty pathogens from your immune system. It literally blocks antibiotics from getting through, and it even lets the invaders inside talk to each other so they can get stronger and more organized. It's a real problem. So we've got these two major villains, excess fibrin and that gnarly slime armor from biofilms. And this brings us right back to our enzyme. Let's take a look at how serrapeptase acts like a specialized tool, perfectly designed to dismantle these defenses.
The process is actually beautifully simple and logical. Step 1, you've got a problem area, an infection, whatever, and it's shielded by that excess fibrin or a biofilm. Step 2, the tool, serrapeptase, is introduced into the system. Step 3, the enzyme gets to work, selectively dissolving that non-living protein shield. And finally, step 4, the underlying problem is now totally exposed, making it vulnerable to your immune system or other treatments. It basically clears the battlefield.
And this, right here, this is the most important takeaway of the whole thing. Just like with the silkworm, the enzyme selectivity is everything. It dissolves the cocoon, not the worm. In our bodies, it takes out that non-living shield without harming our healthy, living cells. That incredible precision is what makes it such a unique biological tool. And because of this unique mechanism, it's been studied for a whole range of things. Stuff like reducing swelling after surgery by clearing out all that protein debris, clearing up sinus congestion by breaking down mucus, and even helping antibiotics work better by dissolving those biofilms we talked about. You see the pattern? In every case, it's not fighting the core problem directly. It's changing the environment to make it easier for the body to do its job. All right, now we need to hit the brakes for a second. This next part is incredibly important. Whenever we talk about something with these kinds of capabilities, we have to be extremely clear about what it is, and just as importantly, what it is not. This is all about setting responsible boundaries. Because its function is so unique, the potential for people to misunderstand it is really high. So let's just be crystal clear about what this enzyme is not. Let's just walk through these one by one so there is zero confusion. Serrapeptase is not chemotherapy. It is not a cure for any disease. It does not kill cancer cells directly. Its job is to remove the protective shields. And it absolutely 100% does not replace standard medical care.
Think of it as a tool, not a standalone treatment.
This quote from the source just nails it. It really summarizes the whole thing perfectly. Its power doesn't come from being an attacker. It comes from being a dismantler, from removing the obstacles that stop the body's own systems, or other medical treatments, from working the way they're supposed to. So this all leads to a really big question, right? If this enzyme has such a cool and well-documented mechanism, why isn't it a household name? Why isn't it used everywhere in mainstream medicine? Well, the answer seems to come down to a fundamental mismatch of models. This table lays out the conflict perfectly. On one side, you have serrapeptase. It's natural, so it can't really be patented. It's off-patent. It works systemically on the body's overall terrain. But the modern medical model, for very practical economic reasons, is built to prefer things that are the exact opposite. It wants tools that are patentable, monetizable, and target one single disease with one single mechanism. Serrapeptase just doesn't fit that mold.
And so what ended up happening wasn't some dramatic conspiracy where it got banned. No, it was what the source calls a quieter form of suppression. It was just minimized. Its mechanism was poorly explained to the public, and it got lumped into the category of just a supplement, which really doesn't do justice to its function as a serious biological tool.
And that's where we're going to leave it. The story of serrapeptase isn't just about an interesting enzyme. It leaves us with a much bigger, more provocative question to chew on. What happens when a potentially useful tool, discovered right in nature, just doesn't align with the economic and structural systems we've built to develop and validate our medicines? It's a question we're thinking about.